So in this clip, we have a look at engines. What is an engine really? What does it really do? Well, basically an engine is an apparatus which converts heat, by burning fuel, into mechanical energy, into work. And there are different ways to do this, and the basic principles are the same for a jet and a piston engine. But let's start with a piston engine as an example. A piston engine is an engine where we have a chamber where a piston moves and that is because there is a certain amount of fuel which is burned here, creates a high pressure, and that causes the piston to move a distance. Let's call this delta x. And here we have this pressure P, which acts on this surface. And let's call this the surface area A. What is then the force on this piston surface? Well, we know that the force is pressure times area. Because the pressure is defined as the force per area, this means the force is pressure times the area of the piston. We also know that the amount of work performed by this force is the force times the way traveled, force times S, and in our example, this means it's force times delta x. Well, if we then fill in what we know about the force, that it's the pressure times the area, we get the equation pressure times area times delta x. And this part is the force, and this part is the way traveled. But we can also divide it in a different way and say that the area times the delta x is also the change in volume, is the delta V. In other words, you can also write this as the pressure times the change in volume. Be aware that V here means volume, not speed. It's the volume, pressure times the change in volume. So the heat generates a higher pressure, the pressure pushes the piston away, and in this way, this pressure and caused by the heat creates mechanical energy, and the amount of work is the pressure times the change in volume, delta V. Well, this is nice if the pressure is constant, but in reality, the pressure will vary, of course. So you will get an expansion will mean the pressure gets lower as when the volume gets larger. So P times delta V is a bit too simple. You might do that for very small parts, and say, okay, for infinitesimal small parts, the volume is constant. But in reality, of course, you have to sum them, and this means that it is the area underneath the graph in the PV diagram, which shows the amount of energy that is performed when the gas expands. And this is the basic principle of how heat is converted into mechanical energy, into work. But of course, this is only one part of the story. If you look at what really happens in an engine, you see it's slightly more complex. We have to look at the different phases. The air first has to be compressed before it can expand, for instance. So that's what happens. First, we let in air via the intake. It's the intake phase. The pressure remains the same there. We just increase the volume by taking in more air. But then the air is pressurized. It's compressed, and this results in higher pressure. And if we then at this high pressure add a heat and increase the temperature, then with the same volume, the pressure increases. And if we let this hot gas expand, if you're in the expansion phase, you will see that now the amount of work created is the area underneath the graph is actually higher than what it was when we compressed it. Well, if we then have expanded the air, then we have reached the exhaust, and there we release the air into the atmosphere, and of course we take in new air which has the atmospheric properties, so we could connect, for the exhaust phase, we could connect the 2 points in this way, even though it's actually not the same air, of course. Now, what is the net effect in terms of work which we have? Because it takes energy to compress the air, and you release it again when it expands. But because we expand it at a higher temperature than at which we compress it, the difference of volumes between those two lines, the enclosed volume, is basically an indicator of the work that we perform. And this also shows some principles how we can increase this. So if you have a higher pressure, you create a higher pressure. If you compress it more, the area will get larger. That's the engine with a compressor. Or if you create an extra heat at the end, if you halfway during the expansion, you decide to increase the temperature even further, you also enlarge the enclosed area and in this way increase the work. So this is the physical principle, but how is this mechanized? What is the mechanization of this principle? Well, the piston engine is an example, but there are different types of piston engines. You can have, you have different, what we just saw is the 4-stroke engine, but you also have had a 2-stroke engine. It's now obsolete. But you also have the Wankel engine, which still is referred to as new, even though it's been around for a while, but it's still seen as something advanced or experimental. And what you now see most of the time is actually the diesel engine, which is also a 4-stroke engine. But the principle there is that the fuel ignites automatically to the thermodynamic situation. So the diesel ignites itself, but apart from that, it's the same principle as a 4-stroke engine. You will find many diesel engines on today's modern general aviation aircraft. If we see if we look at what happens, it's often not in an engine. It's often not just one cylinder. There are different cylinders, and there are different ways in which you can organize, which result in different geometry or layout of your engine. For instance, here we see the inline engine, and this is the type of engine as used by the Wright brothers, for instance. They had simply put the different cylinders in one line, and you see that while one of the cylinders is, or actually two of the cylinders are expanding, they provide the energy via the axis to the other cylinders to compress. And this is how the sum or the subtraction actually of the two different energies takes place in an inline engine. Well, we see the same principle in the radial engine, where by a subtle difference, a different phasing of each of the cylinders, you basically see that every piston is in a different phase of its expansion or compression cycle, and in this way transfers energy to each other by using expansion energy of one cylinder for the compression of the other. And this radial engine is often used when you have many more cylinders than the 5 that we see here in the animation. A variation on the inline engine is what's called the boxer engine, in which the two cylinders are put on opposite sides, and in this way create an arrangement similar to the inline engines. But it's also possible to put them in a different configuration. For instance, the V engine, which is similar to a boxer engine, but has them both slightly up, both sides of the cylinders. And you see here the inline radial boxer engine also indicated. The choice for one of these engines basically has to do with your design, the shape, the center of gravity, or your weight requirements, which determine which type you choose for your specific aircraft. So that's how engines work, both the principles as well as the mechanization. Now let's have a look at what you can do with this mechanical work that is generated by the engine, how we can translate this into thrust. And that's what we'll look at in the next video clips, first for propeller engines and then for jet engines.